All right, we're back again to continue our discussion about series in 11.2. So previously we talked about geometric series, which, as I said before, are very simple. Is a very simple type of series for which we can completely answer basically any question. Now, in general, we're going to be dealing with more difficult types of series where we'll be lucky if we can determine does it converge or diverge. And what I mean by that is, even if we can determine that it converges to something, we won't always be able to tell what its value is. So that we'll get much deeper into that later. But for the rest of this section, I want to talk about a couple other important examples, and at least one important tool to help us determine if something diverges. All right, so first, let's start with a very important example called the Harmonic Series. So this is the summation of 1 over n from n equals 1 to infinity. And this is not geometric. It's not a exponential type sequence. We're not raising anything to the nth power, so it's definitely not geometric. But we want to ask, is this convergent or divergent? So let's look at the sequence of partial sums. And I'm going to want my space to let me erase and write some partial sums here. Okay, so S1 is 1 over 1. That means it would just take the first term of this sequence and stop there. S2 is 1 over 1, which is 1, plus 1 over 2. So we take the first two terms. S3 is 1 plus 1 over 2 plus 1 over 3. S4 is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Let's not write every single one of these. I'm going to skip ahead and put another one in a second, but here's the point. Okay, so I deleted my first attempt at explaining this, so let me start again. So we're looking at this sequence of partial sums, and this is down to S4. I'm going to put another one here in a minute. What I want to do is compare this to a simpler sequence, one that we can more easily understand what's going to happen. Let's start at S3 here. I don't like the 1/3. I want to deal with powers of 2. So what I can say is 1/3 is bigger than 1/4. So this thing is bigger than 1 plus 1/2 plus 1/4. On S4, I want to do the same thing. 1/3 is bigger than 1/4. So this will be 1 bigger than 1 plus 1/2 plus 1/3, or 1/4, sorry, plus another 1/4. So what I want to do is replace these fractions where the denominator is not a power of 2 with the next biggest power of 2. So let me skip to S8. I need to make better use of my space here. There's my first 8 terms of this series. So 1/3 I'm going to replace with 1/4. So what I'm going to have is, I don't have a ton of space there, so let me group these together. This here, we have 1/3, which is going to be replaced with a 1/4, together those are going to make a 1/2. Then the next three of these, 1/5, 1/6, and 1/7, those are all bigger than 1/8. So I'm going to replace these with 1/8 plus 1/8 plus 1/8. Then I already have a 1/8. That's 4 1/8s. Together that makes another 1/2. So this is bigger than 1 plus the 1/2 that's already there. Then these two things are bigger than another 1/2. And then these four things are together bigger than another 1/2. Okay, so this previous one, the S4, I can replace those two 1/4 with a 1/2. And so what we can see, I'm not going to write another one, but what we can see is if I go far enough, I can 1/2. Sorry, that should be another 1/2. So what we can see is I can go far enough to get another 1/2 out of this, to make this bigger than another 1/2. And if I'm always able to add another 1/2, my sequence of partial sums are not going to level off. I can always increase my output, my total, by at least 1/2 if I go far enough out. Come here. Okay, so I don't want to try to figure out the exact formula here. Our sequence of partial sums is a bigger sequence than a sequence where I'm accumulating 1/2s over time. And that sequence is not going to converge. It's going to go to infinity. So something bigger than something that goes to infinity also has to grow to infinity. So my partial sums do not reach a limit, do not have a limit. So that tells me that the harmonic series 1 over n is divergent. So that's an important fact to know. Come here. Stay out of the way. All right, so know the harmonic series 1 over n is divergent. So it's divergent, so it doesn't have a value, so we don't have to worry about computing its value. Okay, another series I want to talk about. This example is not such an important specific series, but the technique that we can use to study it is important. So I want to look at the series summation from 1 to infinity of 1 divided by n times n plus 1. So what I want to do is rewrite this fraction. So this goes back to the beginning of the semester. If you think of this as a function where the variable is n, the type of function we have here is rational. It's a polynomial divided by a polynomial. And our denominator is already factored. I can break this up as two simpler fractions by means of partial fractions decomposition. All right, so it's not integration, but we can still use partial fraction decomposition to rewrite a fraction of this type. So rather than bore you with the details, this decomposes as 1 over n minus 1 over n plus 1. So going from here to here, that's just partial fractions decomposition. You can review that in section 7.4 if you don't remember it, but the technique's not going to be that important in general here. It's just for this specific example we need it. The more important thing is once it's broken up like this, this is a specific type of situation now. And so I want to look at a partial sum for this. SK. I'm going to do it in this form here. Well, I want the first K of these added together. So I start with 1. That would give me 1 over 1 minus 1 over 1 plus 1 is 2. So that's what I get from that term when n equals 1. Now I plug in when n is 2, I get 1 over 2 minus 1 over 2 plus 1 is 3. And so this goes on and on. Can't reach over there right now with the cat. She won't let me. The next one will be 1/3 minus 1/4. And this continues until I get to the last one. When n is k, that would be 1 over k minus 1 over k plus 1. Okay, so this is my partial sum, but there's a lot of cancellation that occurs here. If you look at a consecutive pair, I have minus 1/2 here, plus 1/2 here. Those two 1/2s will cancel. I have minus 1/3 here and plus 1/3 here. Those 1/3s will cancel. So each parentheses shares a number with the next parentheses, and they have opposite signs. So each consecutive pair, there's going to be like this collapse, this cancellation. This is what's called a telescoping series. Like the old-time spyglasses on a pirate ship. You can collapse it, and all the middle parts collapse on each other. Go on. So what's left after all this cancellation? Well, this very first term here, the 1 over 1, that has nothing to cancel with it from before, so we have that left over. And this very last term here, the minus 1 over k plus 1, that has nothing to cancel with. So after the telescoping, my partial sum collapses to just this, 1 minus 1 over k plus 1. Okay, so let me rewrite that. What we have now is a simple formula for our partial sum, so we can figure out what is its limit as k grows to infinity. Well, 1 is constant, so it's not changing. 1 over infinity is 0, so I get 1 minus 0, which is 1. So my series here is convergent, and its value is 1. Okay, so that's a specific example, but the important point to take from this is just this trick, this telescoping trick. When your series, when the sequence inside your series can be written as a difference of consecutive terms of some other sequence. So here we have this 1 over n and 1 over n plus 1. It's the same expression, except one of them has n plus 1 in place of n. So if I have a difference of two things like that, where they're the same formula but with n plus 1 in place of n on one of them, then you have this telescoping situation. Your partial sum will end up simplifying as the very first value of this thing minus the the kth value for the second one. So I plug in k for the second one, 1 for the first one. And so my partial sum simplifies, and then I can hopefully take the limit of it, because it'll generally be a much simpler formula than the partial sums would normally be. Okay, it's not always a partial fractions decomposition that takes you there. There's other ways you can do that for other situations. But the key thing is just showing you the idea of a telescoping series. All right. The next big thing from this section, well, really the last big concept from this section, and then after that we'll do a couple examples with it, is called the divergence test. And what it says, so I look at, let me write like this. I look at a series and there's a sequence that I'm adding up. There's the series, which is the sum, and there's the individual sequence that we're adding up, the ANs that we're adding up. If the limit of the sequence, limit of AN, as n grows to infinity, does not equal 0, then the series is divergent. Okay. Now the idea here is if I want my partial sums to level off, so I just think about constructing this one term at a time. I have A1 plus A2 plus A3. As I add more and more terms, I want this total to level off. So if that's going to happen, if that total is going to level off towards some number, then the things I'm adding, they have to start getting small eventually. They have to become smaller and smaller as we go on. Otherwise, for example, if these terms are approaching something else, like say the ANs are approaching 2, then the more A's I'm adding, it's like I'm almost adding a 2 each step. And if I keep adding 2's, I'm not going to level off to anything finite. It's going to grow to infinity. That's not a proof. I'll sketch a proof here in a second. But you can kind of see that if I want this total to have any hope of leveling off to a value, the things I keep adding have to get small if I go far out here. Otherwise, if they're not small, I'm adding big things, relatively big things, so my total is going to keep growing. Or if they're negative, it might keep decreasing towards negative infinity. What's not clear, though, is if the limit of the sequence doesn't exist, how does that tell us that the sum's not going to exist? So let's sketch a proof. In the interest of space, this is going to just be a rough sketch. So the way we prove this is by proving its logically equivalent statement called the contrapositive, which means I say this conclusion's not true and then prove the opposite of this. So we assume that the series is convergent I want to show that the limit of AN has to equal 0. All right, but I can say this. AN, an individual element of the sequence, AN, it's the difference between two consecutive partial sums. So it's Sn minus Sn plus minus 1. So Sn would be the sum of the first n A's. Sn minus 1 is the sum of the first n minus 1 A's. So if I subtract, I'm canceling all of the A's except for the biggest one, the last one for Sn, which is An. So An is the difference between two partial sums. So if I look at the limit of this, limit of An is going to be the limit of this difference. Well, the partial sums have to converge to something because my series is convergent. If the series is convergent, that means my partial sums have to have a limit. So individually, the partial sums have limits. So I can split up this limit like so. We're taking the limits as n grows to infinity. Well, Sn and Sn minus 1 are essentially the same sequence. You're just numbering them a little bit different. You're shifting the subscript by 1. It's still the same sequence of numbers. So these two limits have to be the same thing because they're limits of the same sequence of numbers. So a number minus itself is 0. So again, what we've said here is if we assume that the series is convergent, then it has to be true that the limit of the ANs has to be 0. Therefore, if the limit of the ANs is not 0, it could not have been true that the series was convergent, so it has to be divergent. All right. So I just wanted to give you some quick idea of the proof. It's more important, though, to be able to use it. And before I get into that, let me point out the biggest misunderstanding with the divergence test. So let me put a caution here. Just because the limit of AN is 0, so suppose I look at the limit of the ANs and it is 0, it does not mean that the series has to be convergent. Okay, this is the divergence test. This test can only tell us that a series is divergent. It can't tell us that a series is convergent. There are divergent series that can pass the divergence test, meaning the divergence test will not detect that it diverges. Okay. So let's look at a few examples. So use the divergence test. For these series. Summation of n cubed over 4n cubed plus n squared. Alright, so the divergence test means I ignore the sum. Just look at the sequence. And I think about what is its limit. Well, without going through the details, because we've seen these plenty of times now, when our sequence is rational, meaning polynomial divided by a polynomial, if the degree is the same, these are both n cubed, the limit's just the ratio of their leading coefficients, so 1 divided by 4. So the limit of this term is 1/4. 1/4 does not equal 0. So I can say, absolutely guaranteed, this series is divergent. Right? So that's all I would have to say about this series. Let's do another one. So if I had, say, summation of 3n squared over 5n cubed plus n. Now look at this limit. Well, if the top degree is big, or sorry, if the top degree is smaller than the bottom, so n squared versus n cubed, the bottom's going to win, and you'll have 0. Dividing by infinity dividing by a higher degree of infinity is going to give us 0. Okay. So the limit is 0. That does not tell me that this series converges. It tells me that the divergence test is inconclusive. Okay, so this series, for all we know at this point, this series might be convergent or it might still be divergent. This test just doesn't help us. Doesn't tell us the answer. Okay, the main point of many of the remaining sections in this chapter are different ways to determine if a series is convergent. The divergence test is nice because it's quick. For lots of series, we can quickly say that series is definitely divergent by this limit test, by looking at the limit of the sequence. But when the limit's 0, the divergence test doesn't help us anymore. We have to figure out a different method to determine the convergence or divergence of the series. All right. So let me write that down just to really drive it home. If the divergence test is inconclusive, so again, there's only 2 possible outcomes for the divergence test. There's the series is divergent or the test is inconclusive. If it's inconclusive, we have to find a different method to further investigate the series. And these different methods are going to be the topics of the next several sections of chapter 11. So let me reiterate this main point. Try again. When the divergence test is inconclusive, that means we don't know whether or not it's divergent or convergent. We have to use a different method to study the series any further. And those other methods will be the topics of the next several sections of chapter 11. We'll start 11.3 in the next video. But let me just mention, for these other convergence tests, the tests that can actually determine that a series converges, they still won't help us answer the question, what's the value of those series? So we'll be able to say, given a certain series, this definitely has a value. The partial sums do level off towards a number, but we won't know what that number is. There will be some approximation methods for some of these situations, or some approximation methods, but we won't be able to calculate the answers for very many of them. So from this 11.2, there is a very small collection of series that we can completely evaluate. Those are the geometric series. We can answer the questions for any of those. Other than those, there are some very special cases like the telescoping situation from earlier that we can find tricks to evaluate the value. But for the most part, we won't be able to answer the question, what is the value of a series, of a convergent series, very much at all. So